Welcome to this Danfoss Climate Solution live stream about heat pumps. A rather hot topic for the time being, I guess. We'll be discussing this from the cooling perspective, because that's what we know best. And you can ask questions. You can do it in the chats, and we may also be asking you questions actually for a change, like in polls on specific topics. But please let us know from where you are joining us when you ask questions. Thank you. Today's panel, we have all the guys, well, not all the guys from Climate Solution, but the guys we have on board today are all from Danfoss Climate Solutions. We have Jörg Saar. Jörg, could you please give us a wave? Thank you. Global Application Manager joining from Germany. We have Morten Skovrup, Global Applications Expert Manager from Denmark. And Jamie Kitchen, Sales Account Manager, North America, or rather Canada, or both. And myself, Jens Andersen, Senior Content Manager at joining from Denmark. Thank you. Now, we'll start with an initial question. And it has definitely something to do with this hot topic. Heat pumps, are they going to save our energy-starving world? Huh? What do you say? Morten, Jörg, Jamie, what do you think?
Well, that's an interesting question, and let me maybe start. For sure, heat pumps can help to heating energy and can help to affect. And when I say heating energy, and I mean not only room heat, domestic hot water production, heat for maybe even industrial processes. Heat pumps can not sell or help everywhere, like to kind of drive a truck with a heat pump, but for heating can help quite a bit. Of course, we still need electricity but then the heat pump gives you a lot more heat output than you put electricity in. So if you have a direct electric heating now, the heat pump can reduce the electricity direct pretty easily, and it can replace gas or oil as well.
Thank you, Jörg. Morten, you were going to say something.
No, I'm not sure I was going to say something, but just to, also add on what Jörg was saying, it is perfectly true that, energy, the energy solution or situation will not be solved by heat pumps. But in general, you could say that all over the world, we need to stop burning fossil fuels to keep hot. And there's basically, at least where I'm from, Europe, Denmark, there's two solutions. One is district heating, where you get the heat from burning something centrally. Could be biomass. It could also be large heat pumps, and then you have individual heat pumps, and that is basically the only two solutions you're looking into, combined with the solar panels, solar heat.
Jamie, what do you think?
In my case, in Canada and in North America, heat pumps really are a solution to issues where you don't have any natural gas infrastructure. So there's large parts of the northeastern United States, western United States, up in Canada, where you don't necessarily have that natural gas infrastructure. So to be able to use electricity, and Canada has abundant electricity. In our region, a lot of it is developed by nuclear and hydro and things like that, hydroelectric. It allows us to use low carbon generated electricity very efficiently. So rather than having to run natural gas lines, thousands of kilometers all over the place, you already have that electric infrastructure. The electricity is already being generated. It's there to use. If you use a heat pump, and you're using a heat pump with a COP of 2 or 3 to 1, which is something we're probably going to have to explain. it allows you to get far more energy out than what you're putting in. So from that standpoint, it does save a lot of energy. It allows you to effectively use electricity rather than having to build infrastructure for another type of energy source. And at the same time, it uses, half the electricity or half the energy input or less to produce the same amount of heat output. And so that's kind of, in my area, that's what's important, I think.
Yeah. I think it's maybe a good thing if we just get to sort of, first of all, get a definition of the heat pump itself. What is a heat pump? Pumping in the first place, and maybe also a quick recap on how the heat pump actually works. And that could be something like what you just mentioned, Jörg. Jamie, the COP. Jörg, you have prepared something, and I think, was it Morten who was going to show us the slides?
Yes.
Please go ahead.
Yes. So start from the beginning. I have just put a few slides together, and all of them, but just to have something available in case we need that pretty good now. So what you see here is a building, and outside of that building, a heat pump, and that heat pump takes heat from the ambient, and that heat is of course free of charge from the ambient air, and increases it, then puts it into a building. That's what the heat pump is doing. Doing that by what, maybe you can jump to slide 4 there, please. And it's doing that by simply taking that free of charge ambient heat, and we need to put some electricity to run it. But the electricity itself is not all the heat. That heat is really just to run the heat pump. And when the heat pump runs, it can take that free heat, which is renewable heat, and then the output is the combined energies of the free of charge renewable, the electricity. That's what the heat pump puts out. And that's where you see only a smaller portion of electricity to drive, to run the heat pump. Output is far, far more than this smaller part of electricity. So kind of a multiplier. You multiply the amount of via electricity and get out a lot of more heat out of that heat pump. And the multiplier is a value, Jamie, that's then called the COP, coefficient of performance. That just tells how you multiply that. And if that coefficient is 3, for example, then you get out, then you put electricity in to make that very simple. Maybe we can come to that later. Hopefully that explains already.
Yeah. Actually, we have a question from Paul-André. Paul-André Filling is asking, is the information based on CO2 heat pumps? And I don't know, Jörg, or somebody else for that matter would like to answer that question, please.
Is the information based on CO2 heat pump? I don't know exactly where the question goes. There are different aspects. One is the energy. So the kilowatt in energy you talk about. And there is no direct CO2 relation, pure energy. That's what you've seen on the screen here. You put a certain, let's say 1 kilowatt hour, then the heat pump grabs 2 kilowatt hours from the 3 kilowatt hours out in energy. When you produce electricity, it depends on how you produce that. This is related. When you burn coal in a fire and then make steam, and you produce CO2 by generating electricity, and that's where CO2 connection comes from. But I don't know whether that's why we talk about the refrigerant CO2 in a heat pump. That's why I question. Maybe you can come back with a bit of information you want to know.
Yeah. I mean, it's a good point. The refrigerant is really the carrier of heat. So, like in an air conditioning system, you're using the refrigerant in the evaporator to absorb heat from a source, whether it's waste heat, it's outdoor air, it's groundwater. So the CO2, the two things, the CO2 is an efficient carrier of heat. It allows better efficiencies, COP, if you want to call it that, than standard refrigerants. Also, CO2 allows a different running method where we run in something's called transcritical, where it runs at higher pressures and temperatures. And if the conditions are right, it allows you to have a much warmer heat, a much higher quality heat available. So CO2 systems, when there is a conditions are favorable for them, they can be a very, very effective source for using as a heat pump. Excellent quality heat that comes off of them.
You can, if the refrigerant, you can basically say CO2 as a refrigerant makes when you need to reach pretty high temperatures. Then
correct, yes.
CO2 gets refrigerants. Below a certain temperature, maybe other refrigerants are better. There's no real one solution. It really depends on what your heat temperatures should your heat pump deliver to the industrial process or to your building heat for.
Yeah, you could also add that CO2, especially in the transcritical operation mode, that it also depends very much on the low temperature of the heat you deliver. If you heat up water, what is the temperature of the water getting into the heat pump? If the temperature is low, then that is beneficial for CO2. But whether it's CO2 or propane or ammonia, they are all very good refrigerants for heat pumps.
Yeah. I mean, what's related? And now let's jump. Let's not talk about CO2, but CO2 related to energy production. Then the calculation can be very simple if you compare, for example, a direct electric heating system and now the electric heating system with a heat pump. Then the calculation in the direct electric heating system, in the past you needed, for example, electricity or 6 kilowatt hours of energy. The heat pump only needs 2 kilowatt hours of energy. The remaining 4 kilowatts come free of charge from the environment. And then you need 1/3, 6 divided by 2. And you need, and by that you reduce your carbon footprint by generating that electricity by factor of 3. If the heat pump is more efficient and and you reduce it by the factor of 4. That's when you compare direct electric placed by a heat pump. If you compare gas heating with a heat pump, then you need, but in fact, in general, it runs similar. I hope that answered the question.
Mm-hmm.
Yeah. Jörg, I don't know if you have a possibility to try reconnect, because your audio is is not behaving very good, to put it that way.
Okay.
So it's just maybe a good idea to try to reconnect.
Okay,
Meanwhile,
I'll try that.
yeah, thank you.
Lots of good questions coming in.
Yeah, there are quite some activities, and I'm not even sure where to start actually, because we have lots of questions I can see, and people from all over the world, basically. Funny enough, I've sort of made notes that quite a few are coming from the more temperate areas of the world. And that's a bit funny when we're talking about heat pumps, but that's all right, I guess. Let's see if I can dig up the first question. There are some quite heavy ones here.
I think there's one coming in the chat, or the first one is from Konstantin Vladut, and I don't know whether that's pronounced correctly. I hope it is, approximately. If that says if COP is coefficient of performance used for heat pumps, where do you use EER? COP is basically a measure of what do you get divided by what do you pay. You use it for refrigeration systems, and a heat pump is also a refrigeration system. But it's just a matter of what do you get. You always pay the electricity you put into the heat pump. So COP and is typically what you use in Europe, international countries where you use the SI system. EER is basically the same thing. It's just in American units.
Yeah, you take the BT, you take the watt to BTU multiplier, and that basically is what it is. So
yeah, so there's a conversion. It's just a conversion between units. So EER you will see in North America, COP more or less the rest of the world, I guess.
I'll take the next question. Asad Mahmoud. 1 and 2 ton split ACs with heating and cooling options are they similar to heat pumps, or is it the same thing when it comes to meeting heat and demand? That kind of is a regional thing. If you're in a temperate climate where you have moderate wintertime temperatures and it's not very cold, if the temperature doesn't go much below 8 or 6 degrees Celsius, then the time heating mode for a system, it can just basically reversing the refrigerant through the system. And so instead of your evaporator being your inside coil, your evaporator becomes your outside coil, and you're taking heat from the air outside and bringing it in. In other climates, like where I live, where it can get down to -20, -25 or colder in the wintertime, a lot of times the heating mode will have several stages, and you'll have a heating setup where you can run the heat pump. But if the temperature gets below a certain amount outside, the heat pump can no longer make up that deficit. And so you then have backup heating, and the backup heating can be anywhere from electric resistance heating to small gas-fired units or whatever it happens to be, but you need that secondary supplemental heat. So I hope that answers your question. But again, it all depends. I think regionally there is that difference.
Right. Thanks, both Morten and Jamie. There's another question here from Kaustub Mota. I am again not sure how to pronounce, but how cost efficient are these compared to electric heaters, even in the long run?
A lot more efficient. But anyways,
Yeah.
I'll let somebody else answer that.
Yeah.
Are you back, Jörg?
I hope so. Can you hear me?
Yeah, we can hear you. Great.
Okay. Well, back to that example of your direct electric heater needs 6 kilowatts, 2 kilowatts to provide the same heat to you. That bill is 1/3. And then the calculation is pretty simple. Assume your electricity bill was 3,000 euros before, now it's only 1,000 euros. If a heat pump costs you, whatever, 10,000, then 5 years. And from then onwards, the heat pump saves you money, 2,000 euros a year.
Mm-hmm. Yeah, so your payback time depends on the initial cost of the installation. Generally speaking, the higher the COP or efficiency of the system, the more the applied cost is, the more the upfront cost is going to be. But it works out.
You could also say, you could add, at least in some countries, that if you get a heat pump above a certain size, and that they actually, where I come from, it's very small, there's actually some yearly maintenance you have to pay for to get somebody out and check if the system is running as it should. Because, well, basically a heat pump is a bit more complicated. It's a bit more technical than just an electrical heater. So it's a good thing that somebody comes and look at your system. That needs to be counted in the calculation, but that'll mean it's a couple of months in the payback time less. It'll pay back very fast to have a heat pump.
I mean, it's a good point, because the quality of the installation a lot of times is almost more important than some of the efficiency points that you see on these units. A poorly installed unit with poor airflow or incorrect sizing and things like that is very detrimental to things like energy efficiency. If you can't get the air where it's needed, if the system isn't sized correctly to meet the load or control humidity and AC and in the heating mode, then you're going to have real issues down the road, and the payback period can become very, very, very long if you ever pay it back at all. In fact, a lot of times the systems can fail early if they're not installed properly, and you actually lose that investment. So the maintenance side, very important, as in the installation quality.
One point which might be interesting as well, depending on where you are and what contract you have. Let's make the heat pump a bit bigger. Let's assume you know watts of heat. Now, electric heater, you can have in the system or in the house, but you need to provide 60 kilowatts of electricity. You need to provide 20 kilowatts. And if the heat pump has a COP of 3, to provide 20 kilowatts, depending on now on the contract you have, you might more attractive price per kilowatt hour, because your peak load is going 60 kilowatts as a peak load anymore. Your peak load is all of a sudden only 20 kilowatts. Less per kilowatt hour. It depends on how your contract looks like, that this can come in as well in that calculation.
Yeah, good point. We have another question from Kanwa Basil. How does the performance of a carbon neutral heat be affected if we have an intermittent power supply? That's a good question, actually. That depends, I guess. Anyone volunteer for an answer?
Well, as a ex-service guy, I can tell you that electrical quality is very important to any refrigeration cycle-based system. So if you're talking about intermittent power supply, if you're talking about an unstable grid where you have voltage fluctuations and things like that, it can cause some issues with the compressor system, whereas I don't think it'd be as much of an issue with straight resistance electric heat. Poor voltage or voltage fluctuations can shorten the life expectancy of the compressor and cause other issues in the controls and things like that. So that would be something that you would need to monitor pretty closely, I think. Gentlemen, what do you think?
Maybe there's another angle to that one as well. What that means, how stable is your system, or how often can you lose? What you said, Jamie, is absolutely correct, and especially a heat pump that heats air direct. If you have, for heating system where water is used to transport the heat around in the building, the heat into the building using radiators, fan coils, and so on, advantage. Because now that water mass in the building and maybe is really giving you a lot of inertia. So utility says, I want to have the possibility to switch your heat pump during peak hours for half an hour. Then you can use that thermal inertia of all that water mass and the buffer tank to live through that. After half an hour even, your heat pump is switches on again and provides heat again. And that can be an advantage because sometimes, again, you get a better electricity if your utility is allowed to do that. It depends, as you can see, your heating system built up.
Yeah.
Let's see. Well,
so now we get into the fluids, I guess.
Yeah, I think so. We have a question from Markus Ederich. I guess it's Germanly pronounced. Which fluid will be present at most equipments in future? And I suggest we, at least initially, interpret fluid as the refrigerant. That's okay with you guys.
And there's also some other questions related to that coming along. I would say, and first of all, there's a huge debate about this around the world, and what is needed and what is not. So let me just start and say, I think that natural refrigerants, they will dominate the market in heat pumps, no doubt about it. We are seeing it already now. Heat pumps for a household, for family houses, is going to be propane, I guess, more or less. Industrial heat pumps will be a combination of ammonia and CO2. And then you will have some high temperature industrial heat pumps where you will take the temperature to 100, 150, sometimes up to 200 degrees. And that market will be dominated by hydrocarbons, flammables. I don't think there's any doubt that that is the direction things are going in.
Yeah, I would second what you just said. Yeah, that would be my guess too if I had to bet on anything.
I know that there's A2Ls and that they also are relevant fluids for heat pumps. They certainly are, and they will also find their place. But the predominant refrigerants will be natural, simply because they're cheap, they are available almost everywhere, and the systems are very efficient.
Yeah, the efficiency side of it is absolutely critical, because that's the whole pivot or whatever focus of these systems, right?
Yeah.
And going to hydrocarbons makes a big difference.
Yeah, and then we can have a discussion, or at least that is a relevant discussion about the service personnel, people who are going to maintain, if we go up in size of heat pumps, people that are going to maintain systems with hydrocarbons, flammables, ammonia. We need trained people, we need skilled people, and that is, I think, that's something that is lacking in general around the world. But there's people working on improving on that also.
Yeah, that's a long-term task the industry has seen for a while. Absolutely.
Oh yeah.
And I don't know if you should jump to the next question from Konstantin Vladut. How do the current electricity prices affect the return on the investment of heat pumps? Yeah, that's a good question.
It depends what you're comparing it to. If you have electric heating, right? As Jörg said, if you're comparing apples to apples, if you have straight electric resistance heating, you bring in 1 kilowatt, you get 1 kilowatts worth of heat. If you have a heat pump with a COP of 3 to 1, you're getting 3 units of heat out for every unit of heat you put in. So you're getting 3 kilowatt, worth of heat out for every kilowatt you put in. Now, if you compare it to, say, natural gas, and you live in a region where electricity is quite expensive, a lot of times electricity per, heating value or energy value can be twice what natural gas is. So now suddenly you have the option of looking in, okay, if I compare it to a furnace that is 96% efficiency or 94% efficient, right? And it's going to cost me this much in natural gas. If natural gas goes up in price 5%, but electricity goes up by 25 or 30% because, the mix of electricity or the mix of generating that you have is, nuclear or something like that. Now it's more difficult to compare because it's, if you're looking at from a straight cost standpoint, if natural gas is substantially cheaper than electricity, your heat pump now is going to have a much longer payback period because instead of $5 worth of natural gas, it's $10 worth of electricity that it's got to use. So 2-to-1 COP is going to be your break-even point as far as cost goes. So that does make a big difference, actually. But again, it's only if you have other energy options.
Yeah, and you kids could say at least in some parts of the world, the gas prices and the electricity prices they are kind of connected. So when one goes up, the other one goes up also, and so the comparison more or less stays constant. But there's also there's a dark horse in all of this, and that is how politicians behave, because they are essentially the ones that are deciding what the price of energy will be, and not just the price, but also what type of energy are we supposed to use. And there's no doubt in my mind that the natural gas that is something that is that we are going to stop using in a foreseeable time.
Yeah, especially on the geopolitical side of things. I know in Europe, I think more of your electricity is generated with natural gas than, say, in my area where
Probably, yes.
we have an abundance of hydroelectricity and huge investments in nuclear power back in the day. So I think 90% of the electricity that we have generated here, anyways, in Ontario and Quebec, comes from either nuclear or hydro. With the rest thrown in is wind and solar.
Yeah. And in Denmark, it's primarily wind, and then there's a whole bunch of stuff coming in. Also, because in Europe we are typically connected to each other, so it's quite difficult to have a look at the electron and see whether it comes from nuclear, wind, or coal, or whatever has been used. We pretty much have everything.
Yeah, that's right. We have a good question from Sunil Kumar. How does the evaporator of a heat pump and an AC differ from each other?
Well, I could kind of be sarcastic and say that if it's in the cooling mode, they're the same. If it's in the heating mode, then your evaporator and your condenser are the same. But I think we need a more technical answer than that. So I'll leave it up to one of you two to dig up an answer.
Oh, well, Jörg left, so.
Oh, Jörg's gone. All right. He went by a new phone.
It depends what kind of system. Heat pumps, and we haven't even touched upon that yet. But the heat pumps come in many different flavors. There's water to water, there's air to water, there's air to air heat pumps. There's you can probably make any combinations, and also the heat source, whether it's groundwater or whatever. So that will make the evaporator look different. It will be different. If you're talking about just a split air conditioning unit, there won't be that much difference.
I think that's what he's referring to be honest with you.
Yeah, and if you have a heat pump where the evaporator is sitting outdoors, you will also have defrost issues. You will have all the normal stuff you have with an evaporator. You will see the same things in a heat pump evaporator.
Yeah. The only thing I'd probably add to that, and this used to be more of a thing than it is now because of the efficiency gains in AC as well. But in North America, a lot of times you have a split system, and your outdoor unit serves as the heat rejection, the condenser in the cooling mode. And a lot of times they have a larger surface area than the evaporator indoors would have in the cooling mode, because you want to reject heat at a lower temperature and pressure. So that when you switch to the heating mode, you now take advantage of that larger surface area that is outside, and this allows you to have a higher evaporating temperature compared to the ambient conditions, because the larger the surface area, the more heat transfer that can occur for every temperature difference and change between the refrigerant and the air, for example. It allows you to raise your condensing temperature. It allows you to have your condensing temperature closer to your air temperature. So it actually allows you to okay, let me back up. It allows you to have your evaporating temperature closer to your air temperature. So it allows you to have a higher evaporating temperature. I confused myself there. It allows you to have a higher evaporating temperature closer to the outdoor air temperature. And of course, when you raise your evaporating temperature, that reduces your compression ratio. And reducing your compression ratio increases your energy efficiency. Yeah, I finally got it out, man. So there you go.
Yeah.
You
But
may-
I agree.
yeah. And we have a question now from a person whose name I'm absolutely I can pronounce that name, Tobias Korsgaard. He's asking, do you think because of marketing, modern heat pumps are branded with a higher COP and only which is only available under specific conditions?
It's
It's kind of like your car. You know, you got a 2,000 kilogram car. Does it really get 5 liters per 100 kilometers? That seems impossible, right? Yeah, but that's only going downhill at 45 degrees.
Yeah, but that is true that COP is given at a certain condition. Tobias has a point, but normally, or at least in Europe, heat pumps are marketed under what you can call a seasonal COP. So they're trying to make a seasonal calculation, which includes different ambient conditions. It also includes defrost cycles because they are part of the thing. It includes different load scenarios, so that it also runs in part load. And all of these things you put together in quite a complicated calculation part, and out come the seasonal COP, and that is the one that is marketed. So the question is probably also, when you buy a heat pump, do you get the COP? And I would say that the current value we are giving out for customers, or heat pump manufacturers are giving out for customers, that's much better value than it was for just a few years back, when they were rating the heat pump at the absolutely most favorable condition.
Yeah.
That is not the case anymore. It's a more realistic value you will see when you buy a heat pump.
Yeah, I agree 100%. It's actually changed much better in favor of actually, understanding what you're actually going to get for your investment. In other words, how efficient that system is going to be.
You can do an economic calculation, and you can kind of trust that, right? It's always difficult because you're essentially predicting what will happen in the future, and at least what I hear from people, that has changed from it could be just a biomass furnace that they have at home where they're burning wood or something else, and they change to a heat pump. Things suddenly get a lot easier. It's easier to maintain. It's easier to control. It's easier. You got apps on your phone where you can control the temperatures and stuff like that. So all of that changes the pattern of how people actually use heat, and then it suddenly becomes difficult to compare before and after, right?
Yeah, true. A question from Sergio Matthew. Do you have water-to-water heat pumps? And what is the maximum output temperature we can reach for a water-to-water heat pump?
Yeah, Danfoss doesn't have water-to-water heat pumps. Just we don't sell heat pumps. We sell components for heat pumps. But depends on what you want. You can buy heat pumps that will I think the highest I have seen, that is water temperatures of around 200 degrees. So they are producing steam. Now you're talking industrial heat pumps. For a household heat pump, I've
What are they
seen.
circulating in those things, man? Mercury or something? 200 degrees.
No. That's just water, just
Okay.
in a different phase. But you can for a household heat pump, and that is probably what Soju is talking about. A household heat pump, you will have temperatures that is typically for the typical heat pump, and that is around 55, 60
Yeah.
degrees.
Yeah.
But if you, especially some of the new propane heat pumps I've seen, they go as high as 70, 80 degrees.
Yeah. I think as far as domestic hot water is concerned, if you're using it to heat potable water, in other words, water that you're going to use in a shower or a bathtub or washing up, it has to be at least, I think, 140 degrees Fahrenheit. And I'm not 100% sure what that translates into Celsius, if it's 50 or 55 degrees. But that is required in order to make sure the water doesn't carry any pathogens such as Legionella and things like that that can cause hazards to human health or people's health. So you have to be able to maintain that, minimum water temperature for safety reasons. Now, if it's for domestic floor heating or whatever it happens to be, then there's, other levels that you can get away with. But the thing to remember is that the higher the water temperature or the higher the high side temperature is in relation to what your low side temperature is. In other words, the bigger the difference in temperature between what you're getting heat from and what you're putting the heat into, the less efficient the system is going to be because of that temperature difference. So we try and make the water as hot as it needs to be, but hopefully not much hotter, because again, your efficiency starts to drop off.
Exactly, and that is what you can say. The big difference between an electrical heater, a gas burner, and a heat pump is that the heat pump's efficiency is basically a function of the operating conditions to a much higher degrees than the others.
Yeah. Can we take the next question from Isanka Ithelopa?
Pola.
I would like to know the recommended lifetime of a heat pump.
Oh man.
So would I.
Yeah, exactly. If you find out, please email the rest of us, right? And then we'll all know.
Yeah,
But I mean, it depends again on it depends again on maintenance and everything else. We'd like them to last as long as possible and not less than what they're capable of. And I know that sounds like a cop-out question, but a system can last 5 years, or the same system could last 20 years. The system that had ran for 20 years had good quality voltage. It had regular maintenance. It didn't run outside of its design parameters. Things like that make a huge difference.
Yeah.
And then, separate from that is, the quality of the components and the manufacturing side. So those two make up the majority of the influence on how something long lasts. So if you ask me, I would say I want it to last as long as it possibly can.
Yeah.
Right. So if it's designed to last 20 years, I want the last 20 years at least. Right. Whereas designed to last 20 years, but it dies in 5 because it was poorly installed, it wasn't maintained, there was poor power to the unit that was never caught, things like that.
Yeah. And that, I guess, comes down to, you said it, maintenance, right?
Yeah.
I mean, that's what it's all about. And installation, of course. Raymond Mate is asking, what are the service factors for working with CO2? Are there any dangers, for example?
A refrigeration system is a technical system. There are dangers, and it should only be maintained by qualified people. I think that it can basically be cut down to that. It's not something you do in your spare time. You need a guy who knows what he's doing. It goes for any kind of refrigerant. I think we also had a question. It was in the chat saying that yeah, but CO2, ammonia is toxic, things like that. All refrigerants are toxic. It's just a matter of the conditions, how you handle it, and the situations you get yourself in. So it's a technical system. It should be handled by professionals. So that doesn't matter basically whether it's a CO2 system, ammonia system, whatever. There's CO2 systems, they have higher pressures, but it's not something that cannot be handled. It's being handled by thousands of installations every day throughout the world. It's yeah.
But professionals, as you said, Morten, and that's so important. If you have a simple electric heater, you can put that into your outlet. You have a socket, you put that into your outlet, done, right? If you have a heat pump and you are not a certified refrigeration person, hands off.
Exactly.
Don't work on the refrigeration circuit. You can change settings or whatever, but do not work on the refrigeration circuit. Only professionals. Very clear statement.
Yeah, completely agree.
Yeah. A question from Konstantin Vladuc. Where do you see the soft starter plus compressor solution in the next 10 years?
Gone.
Yeah, I would say
it's a good point when you think about it, though, because if you look at, if you look at the, in fact, it's very relevant because over the past few years, we have noticed that the, if you look at like the constant electrical usage, say, for example, when people went to LED lights and fluorescent lights, the electrical demand on houses started to drop. All right. However, the issue was the amount of motors that were starting and drawing, locked rotor amps when they started kept these huge spikes in demand centered on certain times of day, when industry started, when industry stopped, things like that. And you would see these huge spikes in electricity that required excessive electricity generation in order to meet that. So in other words, we were generating more electricity than we needed 99.9% of the time. Okay, that's an exaggeration, but to meet these electrical spikes from starting motors. However, if you're going to add heat pumps to that equation, where you have these compressor motors, starting up a lot of times in the morning when people get up and turn their heat up or whatever, and it's going to amplify that, industrial demand spike, it's a big deal. And that's where this soft starter, variable speed drives, things like that can control that inrush current. There's a huge focus on that right now because it really means there's much less demand on the electrical infrastructure. And let's face it, electrical infrastructure these days is very expensive and it's very political. So anything we can do to get around that is a big plus.
Yeah, and just to mention that you said variable speed compressors already, Jamie, and I immediately reacted to that question. Gone. Many heat pumps, especially residential size, small commercial sizes, they use variable speed compressors. And as soon as you have that, you have a built-in soft start. That's how it is with a variable speed compressor. You always have a kind of a built-in soft starter. And that's why you don't need a separate one. And since more and more heat pumps have variable speed compressors, it solves itself. You have them built in.
Another question? A good question, actually. Daniel Gustavo, he's asking, considering a heat pump for water application, is it an obligation to use an electronic expansion valve?
No.
Oops.
The clear answer is no. There is no application whatsoever to use an electric expansion valve. You can use thermostatic expansion valves. That's all fine. And they work fine. And you might even get the same efficiency if you have a certain application range. The broader your application range, That means the broader your temperature changes, the more an electric valve can give you some advantages. But if that is not very broad, that temperature range you're looking at, a thermostatic expansion valve can be adjusted to that and work perfect.
Mm-hmm.
But but that's a general rule, right, Jörg? Has got nothing to do with heat pumps. It's a general rule. It's for any refrigeration system, including
it's a general
heat
rule. Yes, absolutely.
Which you make a good point, is because, again, we have to point out that heat pumps are refrigeration systems.
Yeah.
Every
exactly.
refrigeration and air conditioning system is really a heat pump. You're pumping heat from where you don't want it to someplace that you don't care about, or someplace where you can use it, right? All we're doing in a heat pump is making the flow, reverse, if you want to call it, compared to an AC system where you're absorbing heat and taking it to a place where you actually want to use it. So
yeah, you don't reverse the flow. You just use the heat in a different place. It's instead of using the cold side, you use the hot side, right? You're not reversing anything. It's just a matter of where what you think is beneficial.
Yeah.
What is it that you use? Is it the heat or the cold, so to say?
The cold.
Yeah.
Yeah.
Badly expressed, but anyway.
We get it. Yeah.
Good.
A quick question from Leho Nohololo. Nyombane. It's a
We should
question.
call this. We should listen to Jens butcher people's names for 45 minutes.
that is funny. It's perfectly okay for people to comment on this, I would say.
No one is feeling bad about this, but he's essentially asking, is the heat pump system cheaper than the electric heat?
Yeah.
I guess we've already answered that.
No,
yes, it is indeed.
In application-wise, applied cost, yes. Upfront cost, no.
No.
Yeah, that way. Applied cost, yes. Upfront cost, no. Yeah.
Yes.
Lindsay Nico is asking, alongside initial capex on the kit, where are the manufacturers preparing to do to address these issues? I'm not sure I get that one.
No, what issues? Capital expenditure.
So maybe the question is, what do manufacturers do to get the cost of heat pumps down? Maybe you can rephrase the question in that. I don't know whether that's the meaning. If that's the meaning, well, of course, every manufacturer of a heat pump works as every component manufacturer to offer attractive costs, attractive prices.
Yeah.
And everywhere, wherever you can do something, there's work going on.
Yeah, commonality, economy of scale, ease of installation, things like that. It all adds up.
I have taken the liberty of taking a question from Patrick Martin. What are the benefits for us living in the tropics related to the use of heat pumps? That's a very good question.
Do you need heat pumps in the tropics? I mean, I thought it's warm there anyway.
Yeah, but what are you going to do? You're going to put your pot of water out in the sun and wait for it to hit 60 degrees, man?
Yeah, exactly. I mean, you need hot water anyway, but
hot water heat, I think, would be an excellent opportunity for that as far as that goes, man. Because again, you would have a very efficient hot water heating, I think.
Yeah.
True.
I hope we don't talk about room heating. I hope for you who lives in the tropics. But yes, hot water production is extremely efficient there.
Mm-hmm. Yep.
Yeah, and the questions keeps coming. Let's see. Alan Krantz is asking, in commercial buildings, there are examples with both boiler and AC solutions. Do you see a future for combining these systems in an integrated heat pump? Good question.
Yes.
Oil and
oh yes, there is a future for that, because as we mentioned a few times, a heat pump is a refrigeration system. An air conditioning system is a refrigeration system. So why not have one system to use that throughout the year? In the winter to produce heat for the building, in the summer to take heat out of the building. And there are already a lot of these systems commercially in the market, which use that idea to have that one system used for all these functions, for both functions, and in the meantime, and in addition, dehumidifying as well.
Thank you. You just jumped on my next topic I was going to add, dehumidification. There you go. Dehumidification, or the control of latent energy, moisture, is becoming a huge focus with the increase in fresh air requirements that we're starting to see in commercial buildings and schools and hospitals and things like that, to the point where a lot of times we're bringing in almost as much fresh air as, the return air that we're circulating. And because outside it's very rarely the same conditions as inside, a lot of times you need to treat that air. And if you have to remove moisture, a lot of times there's a necessary requirement to reduce the moisture, but at the same time, you don't want to cool the building down to 12 degrees Celsius to do it. So essentially what you're doing is you're running the outside air through a, dedicated evaporator for dehumidification. And then you're using some of that condenser heat, right? That heat rejection from the system to warm that air back up sensibly, so that when it goes back into the space, it's at a comfortable dry bulb temperature and at a, comfortable humidity level. And you don't want to waste heat with natural gas or electricity or oil or whatever to reheat the air. Why not just use that heat from the system to do it itself, right? And that saves a lot of energy.
And you might also add that just the whole topic of heat recovery, that is something that people are going to hear a lot about in the future, simply because the sort of the thought of a refrigeration system having a condenser standing somewhere rejecting heat to the ambient is not going to be accepted.
No, I agree.
We are gonna look at this heat, and we're gonna increase the temperature with a heat pump, for example, and then use it for other purposes. That is what is being done in supermarkets. That is what is being done many places, where you look at what is
supermarkets kind of led that charge, actually.
Exactly. Yes. So you're looking at what is the heat available and what are your temperature needs, and in between those two, that is normally a perfect fit for a heat pump.
Great, thanks. Question from Alexander Martin. Is R1234 ZE scroll compressor worth for air to water heat pumps? Do you profit from high pressure discharge in this configuration?
That's an engineering question, but I think people are trying to make these refrigerant names as long as possible now, just kind of like the passwords we have to use on our computers.
And he's actually missing
I can't speak
another
specifically to that refrigerant. If somebody else wants to, that's fine.
There's nothing. There's R1234ZEE is typically what you're using, and that is being used in heat pumps. So it's definitely one of the refrigerants that are being considered. Again, for most heat pumps, there will be an alternative propane, CO2, ammonia that is working at least equally as good. But there will be niche things where 1234ZE probably will have its place.
Agree. If we dive very briefly into 1234ZE, there are advantages and disadvantages. The advantage is that your pressure levels for higher temperatures on the warm side are not very high. You can handle that pretty good. That's a nice thing. You can generate quite high flow temperatures on the warm side. The negative one on that refrigerant is that when you have low temperature sources, for example, ambient air in the winter, your pressure inside the refrigeration circuit can fall below ambient temperature. So your pressure is below ambient, which is something that you typically want to avoid. So there are pros and cons for that one.
And there's
so that
also
affects the mass flow then, right? The lower the pressure, the lower the density, the lower
and you
the
need
amount
large
of
compressors
refrigerant.
for that refrigerant, but it is pretty efficient. So there are pros and cons for that.
There's pros and cons, and there's also, it's an A2L refrigerant, meaning it's what is called low flammability, hard to ignite basically. But that is that's also an option too, or a thing to consider when you choose the refrigerant.
Yeah. Thomas Keha is asking, how do you see the potential of using heat pumps for grid flexibility, using the house itself as an accumulator? I guess that takes a good insulated house, first of all.
That's an interesting discussion. If you have a buffer tank in the house, you use the water, but I guess you talk about the house itself, the walls, the stones of the house, the air in the house, and there are really different opinions, because some people say, yeah, why not, to warm up the house another 2 or 1 degree more, and then you use that stored energy. But there are people who say, you know what, if I want to have 22 Celsius in the house, I want to have 22, and I don't want my heat pump to decide that I feel comfortable with 23 or even 24, and then it cools down again. Because we as humans are pretty sensitive to these temperature changes. We notice them. So there are these pros and
You're
cons.
absolutely right. Yes. Yeah.
Yeah.
I think when he said grid, I was thinking that if you look at a variable speed situation, if your grid is nearing its max capacity and you're worried about your voltage starting to drop, which we refer to as a brownout, at least here, if you drop the frequency of a variable speed compressor by 2 or 3 hertz, you're probably not going to see a big difference on the capacity side, for a lot of the reasons that Jörg just said. But your electricity demand can drop substantially with frequency. So, they can control the electricity supply by just, controlling the frequency of your compressor by a few hertz. If that means that, the voltage stays good in the system and there's less chance of problems and things like that, I think that would add flexibility, and it's been investigated. But again, it would require a large investment in what we call smart meters or smart utility meters on your house that can monitor and regulate that. And as Jörg says, a lot of people feel that is intrusive technology.
Yeah. We're sort of at the end of time, but let's take a few questions more. One from Sunil Kumar. He's asking about the 200 degree of water, well, steam. Which material to use in that context, especially the heat transferring?
I think it was me who brought these heat pumps up, right? But there's no special material requirements for 200 degrees. That is handled perfectly by brace plate heat exchangers. If you're using that stainless steel, usual materials, no big issues.
Okay.
You could have issues if you're looking into gaskets, especially O-rings, materials like that. But still, there are solutions.
Yeah, of course. Thanks. Samir Rira is asking, how is the difference between the heat pumps and groundwater heat pumps? I guess it's water heat pumps and groundwater heat pumps, right?
Yeah, I can take this one if you want, because that's something that's in our area.
Yeah.
The big difference is investment. From a residential standpoint, let's talk about a residential small commercial. Whereas normally, if you're putting just an air-to-air heat pump in, or an air-to-air or an air-to-water, your typical contractor comes and installs the outdoor unit, the indoor unit, and sets it up. If you're talking about a geothermal system, now you're talking about heavy equipment. You're talking about excavators and backhoe and tunneling and trenching and, ground drilling type systems. You're talking about intensive heat flow, underground heat flow, hydronic heat flow, heat transfer inside. All these things add immensely to the complication and to the investment that's required by the contractor and the installer to do it right. If it's done right, you can have an excellent system with excellent efficiency. If it's done wrong, you have a complete disaster. And I'll tell a quick story. I was at my daughter's dance class, and the lady beside me found out that I was in HVAC, and she literally started crying because the geothermal system that she put in that cost her thousands and thousands and thousands of dollars was not working. And I spoke to a friend of mine who does geothermal installs, and he says, Jamie, it breaks my heart, but there's nothing I can do for her because everything is installed underground. If it wasn't done right, it has to all pretty much be ripped up and put back in again. So it is critical when it comes to geothermal systems that they're put in by a competent person that does it on a regular basis and has made the investment in training and equipment and personnel and everything else. I hope that answers your question, but that's the first thing that popped into mind.
Yeah, great, thanks. Quite a funny, interesting question from Abe Kumar. Is there any solution for battery cooling or heating?
Yes.
Yeah.
Yes, there is.
Yeah, it is. Yeah.
And there are commercial systems available
Hmm.
which use normal refrigeration systems. In a car, for example, you use the compressor that is used for air conditioning the cabin, the passenger cabin, and you can cool or preheat the battery with that one as well. A bit of a hydronics in between, two heat exchangers in between, but yes, there are solutions out there. So it's again a normal refrigeration system.
Yeah.
Guys, I think there's enough questions and interest here that we could do another show.
I think so too. Yeah.
Yeah.
We have 2 questions more. Are you ready? Set up for that?
Yep.
How much overtime are we? 10 minutes approximately.
Yeah.
Would heat pumps be effective as air conditioning when used for cooling?
Yeah, they usually are. They usually dual purpose, and at least around where I'm from, they're dual purpose.
Yeah.
They do both.
Exactly.
Yeah.
And that's the usual. I mean, the thing you see everywhere, right? That it's
However, you got to be
Yes.
careful in sizing them. You don't want to size them based on just heat, right? If you oversize your heat pump air conditioner, right, so that you match the heat. Now that you come to the air conditioning side, if your air conditioning now is oversized for the heat load, that can cause all kinds of problems from everything from, temperature control, humidity control especially, and your energy efficiency will be very poor.
And just to mention that, if you have a water heat or a heat pump that puts the heat into the water and you pump around the water in your house to radiators, you're not going to do that for cooling, because radiators are not made for air conditioning. If you have
I'm
fan
just thinking
coils,
of it.
that's something different. But a radiator or a floor heating system, you can cool down a little bit, but by far not as good as an air conditioning system, because they are not made for that. You can cool down a bit, but not as efficient as, or not as effective as an air conditioning system.
Using your floor as a cooling medium gives me nightmares just thinking about it.
Yeah, let's stay away from that.
Nightmare and cold feet, right?
Yeah, exactly.
Yeah. Last question. It's from Pablo A. We have installed one heat pump, but it's way too noisy for our family. It goes up above 55 dBs. Do you have any solution to reduce that noise till under 40 dB?
Not for an existing system.
No, unless there's something obvious like it's a fan that's imbalanced or the compressor sitting, it doesn't have any rubber isolators or something like that. Unless it's something obvious that you can identify. Yeah, Jörg's right.
Yeah, I mean, you need to look at it. Is there, as you say, Jamie, is there a vibration induced? Is there a pipe maybe hitting the housing all the time? But if that's not the case and the unit is just that noisy because the design of the unit is that noisy, you cannot do anything.
Mm-mm.
Or only with very, very crazy ideas that you put a soundproof housing around your unit and have additional fans which bring in air and out. Forget it. That's far too complicated.
Yeah.
Great. But I think we are at the end now. We've done 10 minutes more than what we planned to do.
And what
Man.
about remaining questions? We try to, I see we have some,
Yeah.
and I guess we try to answer them somehow if we can reach the person, if we can identify somehow who has asked that question, we can try to answer that later somehow via a social media channel. I don't know.
Mhm.
Does that work?
Or we can hold them for a future episode if you guys are up to it.
Or something like that.
I guess it should be possible to answer the questions through LinkedIn at least. I'm not so sure about Facebook and YouTube if we can do that, but we'll try to answer all the questions that we haven't answered here via the social medias. So yeah, we'll do our best. Good. Okay. So I would just say thank you guys to both Morten, Jörg, and Jamie, and it's been a great discussion, and I hope that people who has listened has learned something from us, from you guys.
I know I have.
Yeah.
Listening to you.
Okay. Yeah. But thank you so much, and have a nice evening and a nice day to you, Jamie.
Yeah.
Thank you.
Thank you.
Gentlemen,
You too.
we'll
Thanks
talk
to
to you
all,
soon.
to everybody who joined, and
Yes.
it was a pleasure.
Yeah.
Thanks.
Take
It was
care.
a pleasure. Yes.
Bye-bye.
Bye.
Bye.